We obtained output characteristics of junction field effect transistor in the last presentation, and now I will explain how we can use JFET as voltage controlled resistor. On your screen you can see the output characteristics. The x-axis is for voltage VDS, drain to source voltage in volts, and the y-axis is for current ID in milliamps. We are calling these characteristics output characteristics because we are having various ID versus VDS curves where ID is the output current and VDS is the output voltage. So we are calling it output characteristics, and these curves are obtained at different levels of input voltage. The input voltage is VGS, it is the controlling voltage. The first curve is obtained when VGS is equal to 0 volt, and when VGS is equal to 0 volt and VDS is greater than pinch off voltage, current ID will become constant. You can see current ID is constant and it is equal to IDSS, and this point on the curve is where the pinch off is happening, and the corresponding x coordinate is the pinch off voltage of the JFET. IDSS and VP is already given for the JFET, and let's say IDSS is equal to 6 milliamps and VP is equal to -3 volts. VP is equal to -3 volts and IDSS is equal to 6 milliamps. Now we will talk about the curve number 2. This curve is obtained when VGS is equal to -1 volt. This curve is obtained when VGS is equal to -2 volt, and when VGS is equal to the pinch of voltage, then ID will remain 0 always. Even when you increase VDS, ID will remain 0. So the last curve is for VGS equal to -3 volt, which is the pinch off voltage. Now I also explained 4 different regions in the output characteristics. The first region we saw was the ohmic region. The second region was saturation region. The third region was cutoff region, and the last region, the fourth region, was breakdown region. Now in this presentation we only have to focus on the ohmic region because we will use JFET as voltage controlled resistor. The region on the left side of the pinch off locus. Now what is the pinch off locus? If you remember the last presentation, I told you when you join different pinch off points you will have a locus, and that locus we call pinch off locus. And the region to the left of the pinch off locus is known as ohmic region. I will shade the ohmic region. This is the ohmic region. We also call this region voltage controlled resistance region. The ohmic region is also known as voltage controlled resistance region. This is the other name for the ohmic region. In this region, JFET can be used as variable resistor. This is very important point. We can use JFET as variable resistor in the ohmic region. Now what do we mean by variable resistor? This means we can increase or decrease the resistance using the voltage VGS, the controlling voltage. So if we change or vary VGS, we can also change the resistance of the junction field effect transistor, and in this way we can use it as voltage controlled resistor. Now we will see what is the relation between the controlling voltage VGS and the resistance of JFET. If you compare the first curve and the second curve, then on decreasing VGS, making it more negative, the slope of the curve is decreasing, and we have to see the ohmic region only. If you compare the first line with the second line, then you will find the slope of the first line is more as compared to the second line, and for the first line VGS is equal to 0 volt, and for the second line VGS is equal to -1 volt. So we can say that slope is the function of controlling voltage VGS, and on decreasing VGS, making it more negative, slope will also decrease. Now we already know slope is equal to 1 by resistance, or resistance is equal to 1 by slope. This implies the resistance of JFET is also the function of controlling voltage VGS. So making VGS negative, slope is decreasing, and hence the resistance is increasing. Very simple. Now we will calculate the resistance at a particular level of VGS. The formula we will use is RD equal to RO divided by 1 minus VGS divided by VP whole square. This is the formula for the resistance at particular level of VGS. RO is the resistance at VGS equal to 0 volt. RD is the resistance at particular VGS. VGS is gate to source voltage or the controlling voltage. VP is the pinch off voltage. Now we will solve one example using this formula. In this example, RO is equal to 10 kilo ohms. VP, the pinch off voltage, is equal to -6 volt. VGS is equal to -3 volt, and we have to calculate RD. So the problem is very easy. RO is given, VP is given, and we have to find out resistance when VGS is equal to -3 volt. So RD is equal to 10 kilo ohm divided by, inside the bracket, 1 minus -3 divided by -6, which is equal to 1 by 2 whole square. And when you solve this, you will have 40 kilo ohms as the value of resistance RD. So when VGS is equal to -3 volt, resistance of JFET is equal to 40 kilo ohm. And you can clearly see when VGS was equal to 0 volt, the resistance was equal to 10 kilo ohm, and when VGS is equal to -3 volt, resistance is equal to 40 kilo ohm. So if you make VGS more and more negative, the resistance of junction field effect transistor will increase. So this is the conclusion of this lecture, and this point is very important. On decreasing VGS, the resistance of JFET will increase, and you can also use the JFET as a voltage control resistor because of this property. So this is all for this lecture. See you in the next one.